Hey everyone, welcome to part 2 of our lesson on the history of chemistry. In the previous video, we left off discussing Dalton's atomic theory. As a brief recap, Dalton said that all elements in their pure forms are made up of small indivisible particles called atoms that are unique to each element. However, scientists that followed Dalton discovered that there's a little bit more to it than that. In this video, we'll be discussing some of the experiments that led to the modern model of the atom. The first of these experiments was conducted by English physicist J.J. Thomson. He created a device known as the cathode ray tube. His device consisted of an evacuated tube with very low internal pressure and a metal electrode at either end. One negative, called the cathode, and one positive, called the anode. When high voltage was applied to these electrodes, Thomson found that a beam or ray of particles emanated from the negative side and went towards the positive side. When an electric field was applied, represented here by positive and negative poles, the beam bent slightly away from the negative side. As a result, since like charges repel each other, Thomson reasoned that the particles in this beam must be negatively charged. Since Thomson was also able to get similar beams from other metals, he concluded that all atoms contain negative particles. He suggested that each atom was really a cloud of positive charge with tiny negatively charged electrons floating within. People said that this model looks kind of like raisins in plum pudding, so they named it the plum pudding model. Our next scientist is Robert Millikan, who conducted the famous oil drop experiment. Here's a diagram of the oil drop experiment. Here we have a stream of oil drops being sprayed into this box, and we have two charged metal plates, one positive, one negative. As the drops fall through this pinhole here, a negative charge is applied to them via X-rays. In this process, the X-rays free electrons from the molecules in the air and they attach to the oil drops, causing a negative charge. As a result, this will create an upward electric force on each drop, since it will be attracted to the positive plate and repelled from the negative one. Keep in mind, of course, that there's also a downward gravitational force on each drop. So by adjusting the strength of this electric field, Millikan could balance out the gravitational force by making these two forces equal. Thus, the drop would remain suspended in midair for observation. The reason why Millikan did this was to calculate the charge that was applied to each drop. Since the voltage and gravitational force were known, and the electric force must have been equal in magnitude to the gravitational force, he could calculate the charges. After doing this through many trials, Millikan discovered that the charges on the droplets were always multiples of the smallest unit. For example, one drop could have 3 times the amount of charge as another could have 5 times that amount of charge, but no drop would have 2.5 times the amount of charge on it. This smallest possible amount of charge that all the other charges were multiples of is known as the elementary charge, and it's the charge of 1 electron. The last experiment and scientist we'll be covering is Ernest Rutherford, who's known for his gold foil experiment. In order to fully understand this one, we'll first have to get a brief understanding of radioactivity. Certain heavier elements can spontaneously emit radiation. There are 3 main types of radiation that we'll be covering, and those are gamma rays, alpha particles, and beta particles. And these are denoted with these symbols. During Rutherford's time, it was known that alpha particles had a charge of +2. That is, twice the magnitude of an electron's charge, but positive instead of negative. In 1911, Rutherford devised the gold foil experiment to test Thomson's plum pudding model. The foil in question was a very thin sheet of gold, and Rutherford expected the alpha particles, which are high in mass, to crash right through to the other side. However, his results surprised him. While most of the alpha particles did pass through, some were deflected at odd angles all around this inner ring. If Thomson's plum pudding model of a larger cloud of positive charge evenly saturated with smaller negative charges was correct, Rutherford's results could not happen. He concluded that these deflections could be caused only by a concentrated center of positive charge that contains most of the mass of the atom. Therefore, in Rutherford's mind, the atom was a high mass positive charge in the center, with the electrons circling about. And this is how the modern concept of the atom's components was born. To end off this lesson, let's go over some basic notation on how we describe atoms and elements. The nucleus of an atom, which is the positive center that Rutherford described, contains protons and neutrons. Let's draw a lithium-7 atom, which has 3 protons, which are positively charged, and 4 neutrons for a total of 7 nucleons. One reason neutrons are important is that they prevent the protons from repelling each other, since they have a positive charge, which would destroy the nucleus. The electrons orbit the nucleus at different energy levels, which we'll talk about in later units. A lithium atom will always have 3 protons and 3 electrons, so its atomic number is 3. The mass number, or total number of protons and neutrons of a lithium-7 atom, is of course 7.